What if the internet could never be hacked, intercepted, or slowed down, ever again? Picture this. Every private message, bank transfer, scientific breakthrough, and critical system is protected, not by fragile passwords, but by the unbreakable rules of quantum physics. Imagine a world where spying leaves visible fingerprints. Trust is built right into the network, and syncing secrets happens no matter the distance. This isn't just science fiction. It's the quantum internet, and it's about to change how we communicate, govern, trade, heal, and discover. It's a future where the communication infrastructure itself is your guardian, not a weak spot. For more tech that actually matters, don't forget to subscribe, like, and turn on notifications. Today's internet runs on classical bits, ones and zeros that can be copied or intercepted if someone finds a weakness. Encryption protects most of our communications, but it's not perfect. A lot of it relies on public key cryptography, math problems that are tough but not impossible to solve. With enough power, especially from advanced quantum computers, today's systems could be cracked. That's the big worry. Attackers might grab encrypted data now and just wait to decrypt it years later, once quantum power shows up. But the quantum internet flips that risk on its head. It uses quantum rules to make channels that instantly show any tampering, turning the weakest points into the strongest shields. At the heart of all this is quantum entanglement, what Einstein called spooky action at a distance. Two entangled particles share a link that no regular system can match. If you measure one, the other changes instantly, no matter how far apart they are. This doesn't mean we can send messages faster than light, but it does let us create secure shared keys. In quantum key distribution, or QKD, any eavesdropping messes with the fragile quantum states, causing errors you can spot right away. Physics itself becomes the alarm system, making secrecy not just about math but about the most basic laws of nature. Despite the hype, the quantum internet won't beam messages across galaxies instantly. Light speed still rules. What it offers is perfect alignment, shared states, synchronized clocks, and encryption keys that can't be stolen without detection. That enables QKD for tamper-proof encryption, authentication that can't be faked, and distributed quantum computing where small processors scattered across the world work as one massive machine. In practice, that means a new level of cooperation and trust in a world where data is currency. This is already moving from lab to reality. Satellites have demonstrated QKD over thousands of kilometers, proving that secure quantum communication isn't confined to short fiber links. Urban fiber networks have delivered quantum keys through existing infrastructure, hinting at integration into current telecom systems. Research is rapidly advancing quantum repeaters to store, purify, and relay entanglement across vast distances without revealing the key, the backbone of a truly global quantum internet. Each experiment adds a piece to the puzzle, showing that this network is more than theory. For you, that means trust baked into the network. Imagine a hospital where vital signs, scans, and genomic data flow securely between specialists with no risk of silent interception. Doctors and researchers could collaborate in real time across borders, assured that no unseen actor is watching. Any attempt to snoop is detected instantly, the keys are discarded, and the channel reconfigures, keeping patient care safe in the background, silently strengthening the trust between doctors and patients. Finance stands to benefit just as much. Transfers, settlements, and trades rely on secrecy and precision timing. Quantum secure key exchange would make those links immune to harvest now, decrypt later attacks, while quantum timing could synchronize ledgers down to trillionths of a second, making transactions not just fast but provably fair. Entire markets could run with new transparency, where manipulation and timing attacks become detectable and correctable. That changes how trust is built in global commerce. Critical infrastructure, from power grids to navigation systems, could become harder to attack. If an adversary tries to inject false commands, the very act of tampering would show up in the physics of the channel. Operators could act quickly, knowing the threat is real, not just a software glitch. This is especially crucial for national defense and emergency response systems, where every second counts and misdirection could be catastrophic. Science will gain a new instrument too. Entangled sensors could measure gravitational shifts, climate patterns, or astronomical phenomena with unprecedented sensitivity. Networks of quantum clocks could map the planet's gravitational field in detail, helping with everything from climate models to natural resource management. Imagine climate satellites not just monitoring the Earth's surface, but feeling the tug of its shifting mass with unmatched accuracy, enabling earlier disaster prediction and more sustainable planning. Challenges remain. Photons are lost in fibers, scrambled by the atmosphere, or blocked by imperfect detectors. Quantum memories can lose stored states in fractions of a second. The solution is quantum repeaters, devices that create local entanglement, store it, and teleport it hop by hop to extend the range. Researchers are experimenting with atomic ensembles, diamond defects, trapped ions, and integrated photonic chips to make this possible. Each path has trade-offs, and the race is on to find the best combination of reliability, scalability, and cost. Protocols are evolving fast. Early QKD schemes have been improved with decoy states to defeat certain attacks. Newer approaches like measurement device-independent QKD shift risky tasks to untrusted nodes, while device-independent QKD certifies security from the statistics of quantum correlations alone. This moves trust away from hardware promises and toward fundamental physics. Each iteration makes the system less dependent on perfect machines and more dependent on the inviolable rules of the universe. In practice, the quantum internet will work alongside the classical one. Most data will still travel over high-speed classical links, but quantum channels will provide keys and authenticated timing. Early systems will blend QKD with post-quantum cryptography for defense in depth, physics plus math together. The hybrid model will ensure resilience while adoption ramps up, creating layers of trust where once there were cracks. The business case is growing. QKD can ride on existing dark fiber in cities while satellites link continents. Data centers may protect their most valuable workloads with short-range QKD. Managed services will sell quantum key streams with built-in monitoring and compliance. Governments, finance, energy, and healthcare will lead adoption, followed by telecoms and manufacturing as costs drop. Over time, quantum secure may shift from an exotic feature to a competitive necessity, the same way SSL certificates once went from optional to mandatory. Standards and policy will matter as much as the hardware. Equipment from different vendors must work together. Security proofs need to be vetted by cryptographers. Regulators will wrestle with lawful interception in a world where undetected spying is impossible. The shift won't just be technical, it will force governments and societies to redefine what privacy, accountability, and security mean in a quantum world. Geopolitics will shape deployment. Nations will build secure cores and connect them to trusted partners. Satellites will carry entanglement across oceans, creating secure bridges between allies. Undersea cables may get quantum channels alongside classical ones, protected by physics instead of fences. This quantum divide could shape alliances and rivalries, just as the nuclear age once did, placing enormous strategic value on entanglement infrastructure. The private sector is racing ahead. Telecom giants are adding single photon sources and superconducting detectors to their products. Startups are building thumbnail-sized chips to generate and route entanglement. Cloud providers are testing quantum key management that fits into existing APIs, making it easier for businesses to adopt quantum-secure services without replacing their entire tech stack. Innovation is accelerating, and competition will drive solutions that bring down costs and expand access. Of course, constraints remain. Photons don't wait, so memories must improve. Trusted node networks work now but reduce end-to-end assurances. Satellites avoid fiber losses but face weather and pointing challenges. Cities require compact, robust gear that works in noisy environments. Progress will come from many small wins, not one big breakthrough. The road to a fully functioning quantum internet will look like evolution, not revolution, with each milestone proving more capability. For everyday users, the first benefits will be invisible. Your phone won't need a quantum chip, but the backbone will feed your apps and banking portals with quantum-secure keys. VPNs will be hardened, firmware updates signed with quantum-derived keys, and supply chain attacks narrowed. Soon, quantum secure may be as expected as SSL is today. Over time, the shift will feel less like a leap and more like a new default, woven into the background of everyday life. Workforce development is key. Beyond physicists, we'll need engineers, product managers, and technicians trained in handling single photons, calibrating detectors, and working with cryogenics. Countries investing early in talent will lead in setting standards and reaping rewards. Universities are already building programs in quantum engineering, and businesses are scrambling to secure scarce expertise. The talent race will be just as important as the technology race. Post-quantum cryptography, PQC, will remain important. Even without a quantum internet, we need algorithms resistant to quantum computer attacks. The safest approach will pair PQC with QKD where possible, creating multiple layers of defense. This way, even if one shield falters, another stands. It's the belt and suspenders approach to digital security. where redundancy isn't wasteful, it's survival. Imagine many small quantum processors linked into one giant distributed computer. Complex simulations, energy breakthroughs, or massive optimizations could be run in parallel across the globe. Cloud services could route entanglement to where it's most needed, blurring the line between data centers and labs. This could reshape research into medicine, climate, energy, and beyond, unlocking discoveries that today's computers can't touch. Privacy won't be perfect. Quantum networks protect contents and keys, but metadata still reveals patterns. Tools like mixed networks, differential privacy, and legal safeguards will still be vital. The point isn't a magic shield, but a much stronger baseline for other protections. In the long run, the quantum internet will coexist with legal, social, and cultural frameworks that keep data power in check. Resilience improves too. Because eavesdropping is detectable, the network can reroute around trouble in real time. Outages can be isolated and fixed faster, and sensing capabilities built into the network itself will monitor its health. Networks won't just carry traffic, they'll diagnose themselves, providing transparency into the unseen forces that keep them stable. Rollout will be gradual. National backbones will first serve research, defense, and finance. Cities will connect hospitals, utilities, and emergency services. International links will follow treaties and alliances. Eventually, quantum-secured service will be as common as dedicated fiber is today, a standard infrastructure layer invisible to the average user but essential to global stability. There will be hype to ignore. Not every quantum product will deliver real advantages. The litmus test: is its security grounded in unforgeable quantum statistics or certified device-independent proofs? If not, it's marketing fluff. As with any breakthrough, distinguishing genuine progress from exaggerated claims will be vital. Still, the direction is clear. Today, trust is conditional. Based on the hope that encryption holds, supply chains stay clean, and attackers get unlucky. Tomorrow, trust can be observable, based on physics that no classical adversary can fake. That shift could make markets fairer, science more open, and personal privacy stronger than it's been in decades. The societal implications are enormous, reaching far beyond simple communication. Zoom out, and the quantum internet is more than a secure network. It's a new foundation for coordination at global scale. It aligns secrets across oceans, synchronizes clocks across continents, links sensors into instruments larger than any single lab, and weaves computing into a fabric that spans the planet. It's the connective tissue of a new scientific and economic era. If the quantum internet delivers, today's web will look like a fragile prototype. The next one is already taking shape in satellites overhead, fibers under our streets, and labs where photons learn to carry not just bits, but guarantees. Its emergence signals not just a new phase of technology but a new phase of trust in human history. Stay close to the edge of innovation. If this sparks your curiosity, subscribe, like, and turn on notifications. This is Tech Mythos.